was on pH and indicators. There was just one question that I gave you with the organic stuff. So the first part was, how do strong acids differ from weak acids in their behaviour in water, according to our Nicias? Well, in Nicias, of course, you would say that a strong acid completely dissociates, whereas a weak acid only slightly dissociates, okay? And then a strong acid and a weak acid in Bronsted and Lowry, you would say strong acid is a good proton donor, whereas a weak acid is a poor proton donor, okay? The next thing they asked you for there then was the conjugate base of sulfuric acid. Now, they're looking for the conjugate base. So this is behaving as an acid. How do acids behave? They donate a proton, so you lose a proton, take away a proton from one to the other. Now, no charge at the moment, minus a +1. Remember, it's always a +1 in the brackets because protons are always positively charged. Naught, minus and a plus gives me a minus when you do that. So that's your conjugate base. They also asked you to get the conjugate base of a general acid, but they do tell you it's a weak acid. So look, put this sort of an arrow in, and weak acids, then again, you're looking for the conjugate base. It's acting as the acid, so it's going to lose the proton. So it's going to be H, or losing the H plus, forming A minus. Which of these conjugate bases would be stronger? Now, do you remember we said the weaker the acid, then the stronger the conjugate base. Remember we said that? So which would be stronger? Definitely the A minus, and explain why. Now, remember we talked about weak acid. So HA, remember, is a weak acid. So the equilibrium lies very much to the left-hand side here, okay? Whereas up here, the equilibrium lies very much to the right, right? 99.9% association. They nearly all dissociate to give you HSO4 minus. So is there much of a tendency for this to accept a proton behaving as a base and go back? No, there isn't. But there is a strong tendency for the A minus to accept the proton and make back the HA again, because the equilibrium lies very much to the left-hand side. Okay. Now, explain the dissociation in water of the base. They want the conjugate base of sulfuric acid. So that's the conjugate base of sulfuric acid, dissociation in water, okay? So you would say there it's going to act as an acid, okay, and lose that other proton. So, and then that proton will go to the water. So this is acting as the acid, and the water is accepting the proton. So that's that. The last part of that question, then you're asked to define pH. So again, remember, it's a minus the log. I would put into the base 10 perhaps, and don't forget the square brackets for the hydrogen ion concentration. They're asking you to calculate the pH of a weak acid. Now, our formula there for a weak acid was Ka times Ma, okay? So to manipulate that formula, then remember you get the square root of Ka times Ma. Fill that in. You're told that the Ka was 6.3 by 10 to the minus 5. The molarity of the acid was a 0.2 molar. So the hydrogen ion concentration there, when you do that, worked out to be 3.549 by 10 to the minus 3. And then you plug that value into your pH formula, and your pH comes out at 2.45. Okay, that's the pH. Now, the next part, then they asked you, what is the concentration of the sulfuric acid? Okay, concentration of sulfuric acid is the same pH. Now, sulfuric acid is a strong acid, okay, so complete dissociation. They told you that the the pH was the same. So the hydrogen ion concentration is going to be the same. So you got the hydrogen ion concentration there in the last part to be 3.549 by 10 to the minus 3. So if the pH is the same, the hydrogen ion concentration is the same. Okay, so that's the hydrogen ion concentration. How would you work out the concentration of the acid? Divide that by 2, because look at the ratio. The ratio there is 1:2. So when you do that, then you'll get the 1.77